we are here to perform the experiment titled redox titration. Redox titration is a titration involving an oxidizing agent and electroplating is the process whereby a thin layer of a metal is deposited on another metal by a process called electrolysis. Electrolysis can also be defined as.
We have waited for 5 minutes. Let us now remove it. As
our project is biogas. As you can see, this is biogas. We did this project a few weeks back, but first let us take it to the final.
Which the other parts will connect it to our extra valve made here.
Go.
Now let us test our gas.
See the gas.
It's getting low.
My name is Oluyami. I am the Deborah from Group Academy School doing practical work in the chemistry laboratory. Before I go on to show you the different methods.
So now we'll be talking on separation techniques. Firstly, what are separation techniques?
Inject it into centrifuging by inserting it into one of these holes. You can see the centrifuge is spinning our test tube.
Next, we have potassium thioxanate, lime water, dilute hydrochloric acid, dilute triazonitric acid.
Cube to our sample. We
made a copper solution by adding about 16 grams of copper sulfate into a 100 ml beaker, making it up with some distilled water.
And the half cell reaction for this reaction is this, and the overall cell reaction is this. This is the overall reaction for the experiment we carried out.
Of mass. The law of conservation of mass states that matter can neither be created nor destroyed, but can be changed from one form to another during chemical reaction.
We are going to put it in our water bath so that it will boil. So we are not to boil.
Students and everyone else, I am Mr. Okemonetunde. You are welcome once again to the second series of our practical chemistry. By the grace of God, this second series is different from the first one and it contains many practical works. This includes two-based experiments on particular nature of matter, flame test, food test, laboratory preparation of some household chemical products, laboratory preparation of indicators from flower extract. Others include experiment on rate of chemical reaction, experiment on solution and solubility. The essence of this video is to facilitate the teaching learning process and to encourage teachers to take their students to the laboratory for real chemistry practicals, rather than dwelling on what is called alternative to practical chemistry or trade of practicals. As usual, I consider it best to use my beloved students for presentation, and I strongly believe we will learn a lot from them. Keep your finger crossed and watch the practicals.
Good day, my name is Confidence Umokalu. With me and my classmates, we are all prospective SS1 science students offering chemistry. Chemistry is the mother of all sciences and experimental subjects. It is a branch of science that deals with the study of composition, properties, transformation, and uses of matter. It has numerous benefits. For example, most of the things we use every day, such as soaps, detergents, pomade, candle, shoe polish, perfumes, nylons, are all made through chemical processes. Studying chemistry provides us with the adequate knowledge on how raw materials are transformed into useful man-made products. Watch as we apply chemistry to make some household products.
Good day all, we are prospective SS1 science students and we are here to make candle.
prospective SS1 students, and we are here to prepare a vision solution known as G.
Prospective SS1 science students, and we're here to prepare black body. Prospective SS1 students, we are here to prepare for a body cream. Good day all. We are prospective SS1 science students and we are here to make laundry soap. Prospective SS1 science students and we are here to prepare liquid detergents.
Good day, we are prospective SS1 science students offering chemistry. You are welcome to the end of the laboratory preparation of household products. Our products are ready for display. Here are the household products we produce using the knowledge of chemistry. Here's a laundry soap for washing clothes and kitchen utensils. These are liquid detergents for washing also, and detergents form lacquer readily with hard water. These are candles for lighting. These are pomades for the body. These are black shoe polish used for polishing our black shoe. These are bleach solutions for whitening our white clothes and also for washing toilets and towels.
Thank you.
Good day all. My name is John Lagan. I am an SS1 student of Hope Academy Schools, Jos, and I'm here with my classmates. And we are here to conduct an experiment on laboratory preparation of indicator from flower extract. First of all, we need to know what indicators are. Indicators are substances that produce different colors when added to acid or base. Examples of indicators are menthol orange, menthol red, and phenolphthalein. I'm going to hand it over to my classmate, Deborah, to continue from here.
Thank you. Before we start preparing an indicator from a flower extract, it is good to know the color change of some two common indicators, such as phenolphthalein and methyl red. These are phenolphthalein indicator and our methyl orange indicator. These are 6 conical flasks. These 2 are containing an acidic solution. These 2 are containing neutral solution. And these 2 are containing basic solution. For example, the color of phenolphthalein in acids is colorless. In neutral solution is also colorless, and in a base is pink. While the color of methyl orange in acids is red. In a neutral solution is orange, and in a base Now, we will be preparing our own indicator from hibiscus flower extract. The materials required are hibiscus flower, ethanol, mortar and pestle, a dropper, a beaker, a measuring cylinder, a filter, and a distilled bottle. Step 1. Put some red petals of the hibiscus flower in a mortar. Then add 6 ml of ethanol. Step 2. Crush the petals with mortar and pestle. Filter the solution to obtain a reddish indicator. This is our step 3. Our indicator from flower extract is now ready. These are base, these are acid, and these are neutral solutions. First, we'll add our indicator to our basic solution. In this case, our base changes to yellowish green. We'll now test our indicator with the acid.
In this case, the color is pink in an acidic solution. Lastly, we will test our indicator with a neutral solution. In this case, our neutral solution is orange. Conclusion. Indicator helps to identify an acidic solution, basic solution, and a neutral solution.
Thank you.
Good day, everyone. I'm Okonachi Melchizedek, and I'm with my mate.
I'm with Sylvia.
Adam Jaffet.
Okay, we're from SS2 in Hope Academy School, Jos. I want to demonstrate experiments on flame test. Flame test is an analytical procedure used in chemistry to detect the presence of certain cations in chemical samples. The idea of the flame test is that sample atoms present in flame emit light due to electronic transitions between different atomic energy levels. For example, the color of calcium ion in a flame is brick red, copper 2 ion is blue, iron 2 ion is green, iron 3 ion is orange brown, sodium ion is golden yellow, potassium is blue, and magnesium is lilac or purple, and magnesium is intense white. Sylvia will be showing us the materials needed for this experiment.
Thank you. The materials needed for this experiment are nichrome wire, conch hydrochloric acid, lighter, Bunsen burner, pipette, and our analytical sample.
First step is to fetch our samples into a petri dish using different spatulas. Okay, this is copper 2 chloride, calcium carbonate, iron 2 sulfate, sodium chloride, potassium permanganate, magnesium ribbon. All our samples have been fetched into petri dishes. This is copper 2 ion in copper chloride, calcium ion in calcium carbonate, iron 2 ion in iron sulfate, sodium ion in sodium chloride, potassium ion in potassium permanganate, and magnesium. Our second step is to clean the nichrome wire with hydrochloric acid and dip into the flame in order to remove any traces of contaminant or previous analytical sample. The next step is to make each of the samples into paste with conch hydrochloric acid. Now all our samples have been made into paste except the magnesium ribbon. The next step is to hold each of the samples with nichrome wire. Now we're starting with copper 2 chloride first. We'll now hold it through the flame. As you can see, the color of copper 2 ion in the flame is blue. For our next sample, we'll clean the nichrome wire with conch hydrochloric acid before use. Here, our nichrome wire has been cleaned and rinsed with conch hydrochloric acid. Our next sample is calcium carbonate, which has calcium ions. Here, the color of calcium is brick red. The next is iron 2. As we can see, iron 2 is green. The color of sodium ion is golden yellow. The next is potassium. Okay. The next is potassium ion in potassium permanganate. Okay, sir. The color of potassium ion in the flame is lilac. Okay, the next one is to determine the color of a cut piece of magnesium metal in the blue flame. Here, the color of magnesium is intense white. Thank you.
Thank you.
Good day. My name is Davina Charles, SS1 student of Hope Academy Schools. With me are my mates, and we will be conducting some experiments to show that matter consists of particles. There are phenomena which are used to show that matter is made up of particles. They are diffusion, osmosis, Brownian movement, evaporation, sublimation, and Tyndall effect. These are coded using DOBEST. D-O-B-E-S-T. D stands for diffusion. What is diffusion? Diffusion is the movement of particles from a region of higher concentration to a region of lower concentration. O stands for osmosis. What is osmosis? Osmosis is the movement of solvent particles through a semi-permeable membrane from a region of lower solute concentration to a region of higher solute concentration. B stands for Brownian movement. What is Brownian movement? Brownian movement is the haphazard or zigzag movement of particles of matter. E stands for evaporation. What is evaporation? Evaporation is a process whereby a substance in a liquid state changes to a gaseous state due to an increase in temperature or pressure. S stands for sublimation. What is sublimation? Sublimation is a change of matter from a solid state directly to a gaseous state without passing through the liquid state. T stands for Tyndall effect. What is Tyndall effect? Tyndall effect is a scattering of light rays. Here are the apparatus for demonstrating this experiment. My classmates will be demonstrating these experiments in a few minutes' time. Please watch.
Good day, my name is Ziza Emmanuel, and here with me are my classmates. Today we are going to be carrying out an experiment on diffusion. Once again, diffusion is a movement of particles from a region of higher concentration to a region of lower concentration. The first is gas jar, the second is distilled water, then potassium permanganate crystals and a spatula. Now the procedure. The first step is to fill your jar with distilled water. Now the second step is we gently suspend a tiny lump of potassium permanganate crystal into the jar of water. After some seconds, the purple solution is formed at the bottom of the jar, which is the region of higher concentration, and slowly spreads or diffuses in the water to form a uniform solution. As you can see, it is diffusing from a region of higher concentration to a region of lower concentration. Finally, we have a uniform solution after a few minutes. This shows that matter is made up of particles.
Good morning, all. My name is Abraham, but with me and my mates, we are here to conduct an experiment on osmosis. The materials needed for this experiment are the beaker, the thistle funnel, retort stand, cellophane paper, rubber band, distilled water, sugar solution, and marker. Now we are starting the experiment. These are the setup apparatus for osmosis. First step, tie a cellophane paper around the wide opening of the thistle funnel with the rubber band. Now let's make use of our setup apparatus. Fill each of the beakers with distilled water to reach 3/4 of the beakers. This apparatus will be labeled A, while this will be labeled B. B is our control experiment, while A is the real experiment. The next step is to fill the thistle funneling apparatus A with sugar solution from its stem and inside the mounted thistle funnel into the beaker. Then lower the thistle funnel into the beaker of water. Mark the sugar level in the thistle funnel with a marker. For our control, which is B, we fill the thistle funnel with ordinary distilled water. Then lower it into the beaker of water. Mark the water level also with marker. Then leave the two setup for about 1 hour. After 1 hour, the level of solution in thistle funnel A, which contains sugar solution, increases, while that of the control remains unchanged. This shows that water contains particles which are very tiny to the extent that they can pass through the holes of a cellophane paper.
Good day all, my name is Manuela Zamani. I am my mate Benjamin Daria. I get to conduct an experiment called binary movement. First of all, what is binary movement? This is the haphazard or zigzag movement of particle of matter. I'll hand it over to my mate Benjamin to demonstrate the experiment.
The materials needed for this experiment are microscope, a teeth pipette, distilled water, and chalk particles. Now the procedures. Step 1. Place some dust particle on a microscope slide. Step 2. Add few drops of water to the dust particles using a teeth pipette. Step 3. Then put your cover slide on the dust solution. Step 4. Mount the slide under the microscope. Step 5. Illuminate the slide and view through the eye lens of the microscope. Observation. The particle moves in zigzag manner in the water.
Good day. My name is Ezekiel Tulunde, and with me here is my classmate.
Hey, my name is Jordan.
We'll be carrying out an experiment on evaporation. What's evaporation? Evaporation is a process whereby a substance in a liquid state changes to a gaseous state due to an increase in temperature and or pressure. I'll be handing it over to my classmates to conduct the experiment.
Thank you. The experiment we're about to carry out is for evaporation. For this experiment, we're going to need the following items: a beaker, methylated spirit, and a hot environment. Firstly, we'll pour some methylated spirit in the beaker and leave it open. Here, the volume of our methylated spirit is 60 ml3. Then we'll place it in a hot environment and leave it for a few minutes. After some few minutes, the methylated spirit in the beaker escapes into the atmosphere.
As you can see, the volume here has reduced from 60 to 20. This shows that matter is made up of particles.
Thank you.
Good day all. My name is Cynthia Mangut and I'm here with Favor Itudu. We are here to conduct an experiment on sublimation. First of all, what is sublimation? Sublimation is a change of matter from a solid state directly to a gaseous state without passing through the liquid state. Now I'll hand over to my partner to continue from where I stopped.
Thank you. The materials needed for this experiment are Bunsen burner, heating crucible, spatula, petri dish, ammonium chloride, ice water, and protective wears, which are nose masks and goggle. The first step is to put the ammonium chloride into the heating crucible. Then we put it on the Bunsen burner and we now heat it also. Now you can see that the ammonium gas is subliming without passing through the liquid state. Now you can see that the ammonium gas is subliming without passing through the liquid state. This is sublimation. Now this water can condense when a cold water is poured into the petri dish and placed on the crucible. Now, as you can see, the ammonia gas is now condensed under the petri dish.
Good day all. My name is Udo Kelechi and with me is my classmate Miles Eze, and together we will be performing an experiment on Tyndall effect. Firstly, what is Tyndall effect? This is the scattering of light rays, and I will now hand over to my classmate to demonstrate more on this experiment. Thank you.
The materials needed for this experiment are torchlight, beakers, distilled water, starch, hot water, and spatula. The first step is to pour our distilled water into the beaker, and this is acting as our control. The second step is to pour our hot water into the second beaker and add our starch. This is our starch solution and this is our water, and the water is serving as a control. The last step, we will be passing our light rays through the two beakers using the torchlight, and this will be carried out in the dark room. The starch solution in the beaker scatters light rays, while the distilled water, which is acting as a control, does not scatter light rays. The matter consists of particles.
Good day everyone. I'm Rafa Hope Yakubu from Hope Academy Schools SS2, and with me today are my mates.
Jan Victor Chun.
Osai Faith. We are here to demonstrate an experiment on rate of chemical reaction. What is rate of chemical reaction? Rate of chemical reaction is the speed at which a chemical reaction proceeds. The rate of chemical reaction can be determined by monitoring the following properties of a reacting system, such as color, change in mass of reactant, pH, temperature, volume of gas evolved, turbidity, and pressure. In this experiment, the evaluation of gas will be taken into consideration. I will now hand over to my mate Victor.
Thank you. The materials needed for this experiment are dilute hydrochloric acid, magnesium ribbon, reacting vessel, syringe, stopwatch, graph sheet, and our writing materials. Before we start the practical, it is good to know the theory of the experiment. This is magnesium in a solid form and dilute hydrochloric acid in an aqueous form.
Magnesium reacts with dilute hydrochloric acid in the following way. As the reaction proceeds, magnesium and dilute hydrochloric acid are used up, while magnesium chloride and hydrogen gas are produced. Now, we start our practical to determine the rate at which hydrogen gas is produced. Procedure. Step 1. Fill the reacting vessel with dilute hydrochloric acid. Step 2. Insert the gas syringe through the lid of the reacting vessel. Before step 3, we need to draw our table of values and get our graph ready. Here, time is in seconds while volume is in centimeter cube. While here, volume is in centimeter cubes and it is on the vertical axis, while time is in seconds and it is on the horizontal axis. Step 3. Put a cut piece of magnesium ribbon inside the reacting vessel and quickly cover it with its lid. Before we start, my mate will be recording our values at an interval of 2 seconds. As you can see, hydrogen gas is being formed in the syringe. The rate is not uniform over the whole reaction. The reaction rate is highest at the start of the reaction and decreases gradually with time, becoming 0 when the reaction is completely used up. Now our reaction is complete. We will now work with our table of values on our graph. Here is our table of value and here is our graph. Our volume is on the vertical axis while our time is on the horizontal axis. Now we plot our graph. The rate is not uniform over the whole reaction. The reaction rate is highest at the start and decreases gradually with time becoming 0 when the reaction is completely used up. From our graph, the total volume of hydrogen gas produced is 9.6 centimeter cube. The equation of our reaction is this. Mathematically, rate is given as volume over time. Here, the total volume of hydrogen gas produced was 9.6 centimeter cube, while the maximum time was 20 seconds. So therefore, rate is equal to 9.6 centimeter cube over 20 seconds, which is also equal to 0.48 centimeter cube per second. Therefore, the rate at which hydrogen gas was produced is 0.48 centimeter cube per second. Thank you.
Good day, everyone. I am Oketona Tomiwa, and with me are Olagbemiro Olaolu, Gian Victor, Oyekon Korede, and Fiafa Hope. We are in SS2. Our practical is titled Measurement of Degree of Hardness in Water. Water is said to be hard if it does not form lather readily with soap due to the presence of calcium ions and magnesium ions in water. There are two types of hardness. They are temporary hardness and permanent hardness. Temporary hardness is caused by the presence of dissolved calcium hydrogen trioxocarbonate 4 or magnesium hydrogen trioxocarbonate 4 in water. It can be removed by adding chemicals such as washing soda or by boiling. While permanent hardness is caused by the presence of calcium sulfate or magnesium sulfate in water, it can be removed by adding chemicals only.
The aim of this practical is to measure the type of hardness in water. One way to measure water hardness is by titrating water samples with soap solution, and water samples may be boiled or treated with chemicals before titrating with soap solution in order to determine the type of hardness, either permanent or temporary. So materials required for this experiment are burette and retort stand, the conical flasks, our pipettes, the wash bottle, our soap solution, washing soda, our Bunsen burner and lighter, our writing materials, our water samples, which are A. Distilled water, B. Pipe-borne water, and C. Well water. Procedures. Step 1. Fill the clean burette with the soap solution. Ensure that the soap solution reaches the 0 mark point and remove your funnel. Here we have 3 pipettes. A is for measuring the distilled water, B is for measuring our pipe-borne water, and C is for measuring our well water. Start the titration with the distilled water, which is acting as the control. Pipette 25 ml of distilled water into our conical flask and place it under the burette. Start the titration with the soap solution, and remember, when titrating, do not look at the burette. Here, the distilled water only requires 0.1 ml of the soap solution to form lather. Now enter your value in the table. Now refill the burette again with the soap solution to reach the 0 marked point of the burette. Now pipette 25 ml of the pipe-borne water into the conical flask. Titrate the pipe-borne water with our soap solution. Here, exactly 2.4 ml of the soap solution. Put your value in your table. Again, refill the burette with the soap solution. Pipette 25 ml of the well water into your conical flask. Then titrate with the soap solution. Exactly 3.8 ml of the soap solution made the well water to form lather. Record the value in the table. From our table of values, the distilled water used only 0.1 ml of the soap solution. Pipe-borne water used 2.4 ml of the soap solution to form lather, while the well water used 3.8 ml of the soap solution to form lather. This shows that the pipe-borne water and well water contain either temporary hardness or permanent hardness, or both. Before starting the second titration, we will boil all our 3 samples of water. Discard all the content in the 3 conical flasks and rinse with distilled water. Repeat the titration procedure once again, using all the 3 samples which have been subjected to boiling. First, we start with the distilled water. Again, the distilled water only used 0.1 ml of the soap solution to form lather. Also, the pipe-borne water used 0.1 ml of the soap solution to form lather, while the well water used 2.5 ml of the soap solution to form lather. Here, our values have been entered in the table of values. For the third titration, chemical, which is washing soda, will be added to the 3 water samples. Add few drops of washing soda into all the 3 water samples and allow it to stay for some hours. Decant the uppermost layer of each of the water samples into different beakers, and then pipette 25 ml each into each of the conical flasks. Then titrate the water samples each afresh with the soap solution. For the distilled water, exactly 0.1 ml of the soap solution was used to form lather. For the pipe-borne water, exactly 0 was used to form lather. For the well water also, exactly 0.1 ml of the soap. Then we enter our values into the table of values. The titration of sample A, which is distilled water and acting as control, remains constant, meaning that it contains neither temporary hardness nor permanent hardness. Sample B, which is pipe-borne water, only contains temporary hardness because upon boiling, it made it to require 0.1 ml of the soap solution, while sample C, which is well water, contains both temporary hardness and permanent hardness. The permanent hardness can be removed by adding chemicals such as aqueous sodium trioxocarbonate 4, which is also known as washing soda, or by adding slaked lime. Thank you.
Good day, all. My name is Tega Desiri from Hope Academy. I'm in SS2 with Mia.
Adeyemi Kadiza.
Today we are presenting an experiment on solution and solubility. A solution is formed when a solute dissolves in a solvent. Mathematically, solution is equal to solvent plus solution plus solute. For example, brine. Brine is a solution of salt and water. A solution can be classified as the amount of solute in a given solvent. Types of solution based on the amount of solutes present are 1. Saturated solution, 2. Unsaturated solution, and 3. Supersaturated solution. An unsaturated solution is a solution that contains less solids than it can dissolve in a solvent at a given temperature. A saturated solution is a solution that contains as much solids as it can dissolve in a solvent at a given temperature. And the supersaturated solution is a solution that contains more solids than it can dissolve in a solvent at a given temperature.
And what are the aims of this practical? The aims of this practical are to prepare a saturated solution, an unsaturated solution, and a supersaturated solution. 2. To determine the solubility of a saturated solution. And what are the materials needed for this practical? The materials needed are 1. Water bath, 2. Beaker, 3. Stirrer, 4. Distilled water, the weighing balance, a calculator, writing material, the spatula, and common salt. Now my classmate Jafet will be demonstrating the practical.
Procedures. The first step is to measure 40 cm cube of distilled water into each of the 3 beakers. A is labeled unsaturated, B is labeled saturated, and C is labeled supersaturated. Here, the water inside our beaker is the solvent, while the solute will be dissolved in sodium chloride. The saturated solution is the determinant for preparing the unsaturated and supersaturated solutions. Because a saturated solution is a solution that contains as much solute as it can dissolve in a solvent at a given room temperature. To find the exact mass of sodium chloride that will form a saturated solution in 40 ml of distilled water at 30 degrees centigrade. We'll first weigh our beaker B on the weighing balance. Here, the weight of our beaker B is 76.03 grams. We then put our values in a table of values. The next step is to place all our 3 beakers in a water bath. This water bath is set at 30 degrees centigrade. Begin to fetch the salts little by little into the beaker labeled B, that is unsaturated solution. Stir and continue to stir until the water just no longer dissolves the salt. Here, the salt completely dissolved. That means it is unsaturated. You then add more salt and continue to stir again. Once again, the salt totally dissolves. You add salt little by little till the water no longer dissolves the salt. Here we have obtained our saturated solution because the water no longer dissolves the salt. This solution and the beaker will now be weighed. The weight of the beaker plus water plus salt is 83.25 grams. To find the mass of sodium chloride that completely dissolved in 40 ml of distilled water at 30 degrees centigrade, we subtract this from this, which is this. 7.22 grams of sodium chloride is needed to form our saturated solution. To form an unsaturated solution of sodium chloride in beaker A, simply weigh any mass of sodium chloride less than 7.22 grams and dissolve it. To form a supersaturated solution, simply weigh any mass of sodium chloride greater than 7.22 grams and dissolve it. The second aim of this experiment is to determine the solubility of a saturated solution. Solubility is the amount of solutes that will saturate 1 dm cube of a solvent at a room temperature. Mathematically, solubility is equal to mass over molar mass times 1000 over volume. For example, the solubility of sodium chloride can be determined from its saturated solution B. Here, 7.22 grams of sodium chloride dissolves in 40 cm³ volume of distilled water. Applying the solubility formula, the molar mass of sodium chloride is equal to 23 plus 35.5, which is equal to 58.5. This is the mass of salt, molar mass of salt, and volume of water. Therefore, the solubility of 7.22 grams of sodium chloride in 40 ml of distilled water at 30 degrees centigrade is 3.085 mol per dm³. The solubility of sodium chloride in water can be affected or altered by increasing the temperature or adding more water. Thank you.
Good day everyone, my name is Florence Jongian and our practicals is on food test. Food substances are into different classes. These include carbohydrate, protein, fat and oil. The presence of carbohydrate, proteins, fat and oil can be tested by using chemical reagents such as iodine solution, concentrated nitric acid, Millions reagents, Benedict solution and Sudan 3 solution. Now Osafe will be carrying out the practicals. Thank you.
Thank you, Florence. The materials required are test tubes, beaker, mortar and pestle, wash bottle containing distilled water, chopping pipette, stirrer, spatula, filter paper, pipette, petri dish, water bath, our reagents, and finally our food samples. Our first experiment is to test for the presence of starch in food samples. These are our food samples. The first is bread, the second is rice, the third is beans, and the fourth is egg. Beans and egg are acting as our control. The reagent used for testing the presence of starch is iodine solution. Now we'll be applying some few drops of iodine solution on our food samples. The first is bread. A blue-black coloration is formed when iodine is added on the bread, indicating that starch is present. The second is our rice. Also, a blue-black coloration is formed when iodine is added to rice, indicating starch is present. The third is beans. No blue-black coloration is formed when iodine is added to beans, indicating that it's not a rich starch food. The last is the white egg. No blue-black coloration is formed when iodine is added to egg, indicating that it's not a starch-rich food. In conclusion, bread and rice contain starch. Our next experiment is to test for simple sugars such as glucose. Benedict solution is used to test for simple sugars such as glucose. It is a clear blue solution of sodium and copper salt. In the presence of simple sugars, the blue solution changes color to green, yellow, and brick red depending on the amount of sugars. Other reagents that can be used. Now we'll be testing for glucose. Here's our glucose solution. Our control will be an egg solution, which will be prepared using our mortar and pestle. Here's our egg solution. Now add few drops of Benedict solution to the glucose and egg solution. Place them in the water bath to boil for a few minutes. After boiling for a few minutes, a brick red solution is formed in the test tube containing glucose solution, while no brick red coloration is formed in the test tube containing egg solution. This is the test for glucose or reducing sugar. The next practicals is to test for fat and oil. Oil is soluble in ethanol, kerosene, but not in water. Oil is soluble in ethanol, soluble in kerosene, but not soluble in water. The next is filter paper test. The appearance of translucent spots on the filter paper indicates the presence of oil. Other test for lipids is the use of soda 3 solution. The oil solution is stained red. This is the test for lipids. The next experiment is to test for the presence of protein in food samples. Here we are making use of egg. The first step is to make an egg solution. Here is our egg solution. Then we apply few drops of Millions reagent. A white precipitate is formed. Then place it inside the water bath. The white precipitate turns brick red on boiling. This is the test for proteins. Thank you.